Welcome to Hyfindr Tech Talks. My name is Steven. Today we'll be talking about PEM fuel cell stacks. Now, this has been around for a while, but it's 2026 and there's been so much development going on. And we want to see today how to operate them, how to take care of those little challenges. And for that, we have an expert here today from EKPO Fuel Cell Technologies, a company that, as the name already says it, is deep into that subject. And they have wheeled out one of their experts who does the application engineering there. He has a PhD in chemistry. He has gone through all angles of this and also seen a bit of the history of this. So it's my great pleasure today to welcome Joe Scherer from EKPO. Joe, welcome. Great to have you on the show.
Thanks for having me.
Before we go into the deep stuff, tell us basically, how do PEM fuel cells even work?
They're quite simple, yeah? If we just look at this sketch.
Yes.
So as you know, fuel cells, they need hydrogen as a fuel.
Right.
So we have the hydrogen entering the cell over the channels of the bipolar plate.
Okay.
And then this is transferred to the catalyst layer on the membrane. So there we have a sketch of the membrane, which is conducting protons. So at the catalyst layer, the hydrogen is split into protons, H+.
Yes.
And the electrons are then conducted to the next cell. So on the other side, we have the oxygen with the air coming in,
Yes.
also distributed on the catalyst-coated membrane. And then the protons coming through the membrane are then reacting on a second catalyst layer with the oxygen, and it's just forming liquid water or water steam.
Okay, so basically this is the basic schematic that we all know, and this is still more or less the same.
It's the same since ever, and also different technologies.
Yes.
They're just different on the membrane or the electrolyte what we use.
Right.
Not depending on high temperature or low temperature fuel cells.
Okay, so how does, this is obviously a schematic and this is the very principle of fuel cells. How does this then look in real?
Well, in real, it looks like this. So there we have a bipolar plate.
Yeah.
In this case, what we do is metal bipolar plate. So here we have the active area and the flow field. And here we have the hydrogen inlet to this cell. And this is then distributing the hydrogen over the complete area of the membrane, which we show later.
Okay.
So hydrogen is entering here, is distributed, exiting here.
Yeah. Okay.
So on the opposite side,
Yes.
we have similar for the oxygen. So the air is entering, is distributed, and is exiting here.
Right. Okay. Okay.
As we also produce heat in the reaction, we need coolant. So coolant is entering here between the two layers. What we actually see is two layers of stainless steel, which are stamped and then laser welded together. And they have in between some volume where the coolant can flow and can cool down the chemical reaction.
So actually, we're seeing this is the bipolar plate,
right?
And this kind of sits on top there, right? Exactly. So that and that then supplies. I think what's really nice to see and what I already noticed is these little teeny weeny channels, and we're going to try to show this in the video later. But you have the big hole there. You see it's going in right there.
Yes.
Yes. And for the cooling, is same. I think it's right there, and for the hydrogen, it's same going in there. Obviously, this kind of pops out on this side.
Exactly.
Supplies, and for the oxygen pops out, or the air pops out on the other side. Joe, you brought a video which I quite liked, because that will allow us to understand the setup here. So what do we see?
This is a complete stack. We just removed the housing. We now remove the compression system that keeps the stack together. So what we see in orange is a high voltage connection. We have also cell voltage monitoring, which is controlling the cells. We have a plastic end plate on the other side. And then we just remove the housing cover, and also this, what we call here, is a media supply assembly. We come later to that more in particular, where we have control over the media. We have some pressure sensors and temperature sensors included. But what's more important is coming to the active cell block, what we call it, which is a stack. Here we see a complete single cell. So this means the bipolar plate, this is the so-called MEA. You just see it then. So this is the GDL, gas diffusion layer, the catalyst-coated membrane, another gas diffusion layer, and then the bipolar plates. And as we already said, the bipolar plates consist of 2 layers of stainless steel. And this is then stacked together several hundred times, so 335 of these cells in the cell block gives 123 kilowatt
All right.
power, which is enough to power a passenger car, for example.
Okay, so if one were, let me say, ordering a stack,
Yeah.
they would get a complete set like that. Obviously, I mean, something I learned also, stack comes from, putting the cells on top of each other, stacking them.
Exactly.
And that's how we got to the stack.
Yeah.
Okay, so that was real fast from the schematic to this. Tell me, Joe, how do you then actually operate this thing? So what do you need to do to make this thing work well, get good performance, and obviously long life out of this? Yeah.
Right. It's certainly we need to supply both gases, so the hydrogen and the air, to the stack.
Yeah.
The air in particular is humidified because the membrane needs water to conduct the protons. And then we also supply the coolant to the stack, and this is somewhat controlled with this MSA, what we take care about. So we preheat the hydrogen, we control the pressure of the hydrogen, for example, and we distribute the air and the hydrogen through the stack introduced by the MSA. So you need to supply the gases, you need to supply the coolant, and you have to then remove certainly the high voltage, which these taps what we see.
Okay, so that's where they're connected. So this is the high voltage, basically. Basically they're connected in series.
Yeah.
So you're just plugging at both ends,
Exactly.
and then you connect it. Okay.
The topmost anode gives the plus pole,
Yeah.
and the minus pole, and the plus.
So you said this very elegantly now, but I think it's also about like managing that now. Can you always take as much electricity as you want? Okay, like how much cooling do you have to do?
Yeah.
What are some of the things that you especially as you do the applications?
Yeah.
What are the challenges that we see, and how do you optimize that?
Yeah, it's really important that you supply enough media of all of three with relationship to the current you want to draw.
Okay.
So if you draw more current, then you have hydrogen present, for example.
Yeah.
This will lead that the hydrogen will completely consumed.
Used up,
and then you have the bad word of fuel starvation. And this kills the cell.
Okay. Okay. When it doesn't want to starve. Okay. So what you gotta then push in more hydrogen.
Exactly.
Okay. Okay.
Exactly.
And what about on the air side? Can that happen on the air side as well?
Yeah, but in this case not so severe.
Yeah.
So just then the performance drops.
Okay.
So the cell voltage is dropping if there's not enough air. But then if you want to have the full performance, you need to supply enough air.
So actually you're managing the performance by how much air you're putting in.
Both.
No, both. Or both.
Yeah,
Okay. Okay. And what about the temperature? I mean, you mentioned I think this middle hole here for the cooling. What about that?
So typical temperature is at the inlet 65 degrees C.
Yeah.
And at the outlet 85 to 90 degrees C. With our new designs, with our new bipolar plates and MEAs, we can allow even up to 105 degrees C at the outlet for short term. So for example, if you have a heavy duty truck traveling uphill, you need more power. And you need to have more ability to reject the heat. So that's why you allow 105 degrees C at the outlet for a short time.
Ah, right. Okay. So, I mean, just think of that. So the truck traveling uphill, means that this thing is also changing in situations.
Sure.
Out of the operations, tell us some of the challenges. Like about angle.
Yes.
So this thing no longer as on the CAD like this, now like this.
Yeah.
Is that a problem?
It could become a problem.
Yeah.
So some of the stacks are put like this. So the plates are sitting horizontally, what we call pancake.
Yeah.
It looks like pancakes.
Yeah.
So if you then look at the stack, if it's tilted too much and the water is, for example, rejected from the cell at the topmost part, you don't get the water removed from the stack. So
so it's kind of piling up in there.
It could be piling up at the low part of the stack.
Yeah.
In some cases, we have for example, in passenger cars, the stacks are in this direction, what is typically called toast.
Yes.
And in this
toast, pancake.
Yeah, it's all about breakfast.
Nice.
So again, this is the issue. If we have the lower part and we want to reject the water here, it's difficult to remove it from the stack in this direction.
Okay.
So there's some limits.
Yes.
We test this. Also, all of stacks are tested to the limits, and we can, depending on the stack design, go up to 30 degrees inclination in all directions So we give enough space for uphill, downhill.
And your challenge in operation is obviously to always supply the entire area nicely with all the reactants needed, so that you have a nice uniform reaction here and good performance coming.
This is mainly in the design of the bipolar plate.
Right.
So I always have the saying that for me the membrane is the engine and the plate is the fuel. You have a high performance engine, you need a good fuel to really run it to the utmost. On the other end, if you have a high performance membrane, you have a bad fuel, you cannot get full performance.
Okay, so you've been in this for a while, and we've talked about some of these details now. Has this changed over time?
Yeah, so when I started out my interest into fuel cells going back to 1998.
All right.
So I was also doing MEA, so applying catalysts to membranes. At that time, a membrane called Nafion 117 was the global standard, and that was at that time 180 microns thick.
So this is this part now. No?
It's the part in between even. Yeah, so we don't see it actually. It's a very small, very thin layer in between.
Just you explained this earlier. This is laminated so we can handle it more easily. You know, obviously it wouldn't have this. It would be more or less sitting on there. In this way. Yeah. Okay.
Right. So after a while, turn of the century, the company DuPont brought Nafion 112. It's called.
Right.
It's already thinned down to 51 microns.
Right.
Much more, as half of it. And just for comparison, this is the typical thickness of a human hair. So already at that time, the membrane was only as thin as a human hair.
Okay.
And on both sides, hydrogen and air, and just separated by this thin membrane.
This is in 98. Okay.
And around about 2000. And if you come to today, it's even thinner. So today, company like Gore, they do membranes with 8 to 12 microns. So a fraction of a human hair. You can see there's even reinforcement inside to stabilize the thin membranes. And there you see the electrodes, so the cathode and the anode catalyst layer on the membrane.
Why would you want them thinner all the time?
Because the protons, they have to travel through the membrane, quite a lot of them. And if you go thinner, the resistance of traveling through the membrane becomes lower. And by that, you increase the power density.
Right. Okay. Lower resistance.
Right.
Probably also less heat. Maybe?
Exactly.
Yeah, okay.
Resistance is always turning power into heat.
Yeah, okay. So you get better performance. Okay.
Yeah. So this is due to the performance of the MEAs, but also to the thinness of the bipolar plates nowadays. And also if you come from the catalyst layer, so we have reduced, the industry has reduced the catalyst amount we need for this performance from 3 to 5 milligrams down to 0.3 milligrams per square centimeter of active area.
Okay. Wow. So this is this is sitting on top of that, and I'm just going to lift this up here. So this is the setup that you have. Okay. And now I know that there are different kinds of fuel cell, let me say, types. Yeah. You brought a metallic plate with you today, yeah? And you guys are doing that. There are also carbon ones. We've also had a video here where we talked about silicon. Can you tell us a little bit about that? What's the difference between them, and why would one go for this one? I mean, you guys go for this, so you probably have good reasons.
So at the beginning, when we started out with stacks, we have both. We have composite plates as well as metal plates. But as we focused on the automotive and mobile application market, we know that we have to go very high in power density. And also in stability. Because the requirements of a moving mobile, like a truck or a passenger car, you have to be very highly shock resistant. So for example, easily if you travel over a pedestrian block, you can introduce up to 50 G into the stack.
Okay, so really something shaking, hitting hard shocks. Okay,
And this is one big advantage of metal, that it's really stable. So it's no issue. If you do this with a composite, it will definitely break.
You mentioned that happens in automotive. Do you guys also do rail systems? Okay, because I heard the biggest G's. I don't know if this is correct, you tell me, but I had the biggest G topics you have in rail.
It could be, exactly, because this is a metal wheel running on metal tracks, so this could be also quite hard. And this is one advantage of metals. People are just challenging metal with respect to, we don't use corrosion, we only call this discoloration. So if you control the chemistry within the plate, so as you can see, there's a coating on top of the plate.
So there's coating on top of it.
The dark color shows the coating. And also if you control, for example, the
this is not coated?
Yeah, in this case, it's not coated.
Okay.
But it's also not an issue.
Yeah.
So also if you control the chemistry of the seal, for example, as you can see this in pink, this is a thin rubber layer on top of a metal seal. And if you control this chemistry, because this is all designed by us, you can reduce the impact to the metal. So if you just go for a Home Depot and take some silicone from there, you definitely will fail. So even a good bipolar pool will then discolorate.
Okay. So that is key to managing the corrosion topic is the coating,
right?
And how you seal and how you manage the whole stack.
And also operation time.
Operation. Yeah. Okay. Right. Okay. Because that's also what when we're designing systems, that's some of the things that talk about metal. Yeah. Can have some corrosion topics, but you're saying now that
if you do things right, you can easily come to 25,000 hours of operation. This is what we currently guarantee. Even for our latest systems, or stacks, we guarantee that. And we also don't find metal ions in the membrane.
Okay, so we have shock. We've taken care of the corrosion topic. What other differences are there that we haven't?
As already mentioned, it's power density, because we can go very thin. So we have cells which are in total thickness, membrane plus bipolar plate below 1 millimeter.
So you say we can go thinner in metal than the others. Okay.
Yeah.
Just because of the nature of the material.
Exactly. Yeah.
Okay.
Also, what is a big issue is freeze starting, because the heat conductivity of metal is much better than composite. The freeze start behavior is more superior on metal plates.
Is it?
Yeah, it is.
Okay.
And also you mentioned the hydrogen permeation is also a topic, because if you go very thin in composites, the hydrogen can penetrate through the plate. So it could be that from the anode side, from the hydrogen side, it could penetrate into the coolant.
Okay. Into the coolant. Okay, and then you would have hydrogen in the coolant, which
you have sparkling water in the coolant. Yes.
Okay, you wouldn't want that. Yeah. Okay. So, well, the temperature part, that definitely, you say you have conductivity, obviously, so that means you are able to warm up the stack more quickly, or basically just manage temperature in general, maybe than it is then.
Exactly.
Okay, so these are the reasons why you guys have completely swung to metal. Okay.
Yeah. Also, if we come to series production, because this metal plate is just stamped on a press, and it's only 1 second to form the complete plate, or even seal it. So when we integrate the metal seal, into this plate is only 1 second operation. And all the other stuff is just running with a few seconds. Whereas composites, they have to be cured in a hot tool. And this takes more time for production. So at high volume production, the cost would be lower on metal plates.
Okay. In comparison to composites, or what some people call carbon.
Exactly.
Plates. Okay. The silicon angle we haven't completely talked about. I guess this is just evolving technology. We also had a video on that one. But great that we've come down to this page. I think the silicon guys say that they are able to do even finer channels on this.
It's always the question to what they compare it. Because we have, even in this plate, which was developed together with the ZSW in Ulm, the Hyfindr plate, we have here a channel pitch, so the distance between two landings is below 1 millimeter. So we are at 0.9 millimeter roundabout in the middle of the channel. And it's also a limit, because you have to push the gases through, and also you have to remove the water. Sometimes they form liquid droplets, and they have to be removed. If this channel is too narrow, they get blocked, they get stuck in the flow field. And if you have a droplet stuck in the flow field and there's no hydrogen beyond that, you will have a severe issue with the membrane behind that droplet.
So you're saying there's a limit as to how small and everything they can get. Okay, cool. Well, thank you for sharing those insights. It's always great. I'm sure there are applications where the other ones will fit better. I don't know, maybe stationary or whatever. Okay. Now, we said earlier, you guys have this extra thing on the stack, and let's talk about that. You also brought it here, so actually we didn't say that in the intro. It's a big one here. Tell us what is this and why?
So the media supply assembly comes from the idea, if you look at a complete system, what you see marked in red is the travel path of the hydrogen.
Okay.
So if you put this into your system, you have to do a lot of tubings, you have a lot of connections, different parts stuck in there, and there's always the issue, all of these junctions, they have to be perfectly sealed. Because it's hydrogen, it's a flammable gas, you have to protect it. So what we do is we take all this functionality and put it into one part which is directly linked or directly mounted to the stack. So we have different functions in there. So we come more in detail on the real part. So the hydrogen pathway is completely integrated into this part, coming in here, preheated, pressure controlled, and also dehumidified because there's water coming from the stack. We have to remove that. And then we just put it through a recirculation pump back into the stack.
So you're saying literally 70-80% of your hydrogen loop is sitting right there on this thing already.
Exactly.
Okay. And that is obviously makes it easier to integrate into other systems and reduces complexity.
Exactly.
Okay. And is it the same for the other loops as well, or it's mainly focusing on the hydrogen?
On the other loops, probably you can directly turn to the part.
Okay, cool. Let's move right over here. Okay, here we go. Yeah. Okay.
So already mentioned, coming back to the hydrogen part. So there's the inlet of the hydrogen.
Okay, so you would connect the what would you connect here? The tank?
It's the tank with some lowered pressure. So we allow for 16 to 20 bars inlet pressure.
Okay, so all I'm doing from the tank, just get a pressure reducer, 16 to 20 bar, come in here.
Exactly.
Just deliver it. Okay.
Hydrogen is moving downwards. Here is a heat exchanger included, which is preheating the hydrogen in cold winter times, for example.
Yes, that's thermal topic we had earlier.
Yeah, and then it's coming to the pressure control valve. You can see it from
here. Yeah, okay.
And there we control the flow of the hydrogen according to the amount what we consume. We talked about earlier.
A solenoid?
It's a solenoid, exactly.
Okay, right.
Controlled with this pressure sensor right here. And then the hydrogen is then distributed into two stacks. What we have to think about, because this is our NM12 twin MSA, we have two stacks sitting in parallel.
Okay, so they're basically kind of...
Exactly.
On the other side. And this is at the bottom.
It's at the bottom because we have to remove also the water. The water follows gravity.
Right.
So it's easier if we have all this assembly at the bottom.
So it's actually at the, like your old style oil-based oil bladder.
Exactly, the oil plant.
Okay.
So
right.
If hydrogen comes back from the stack, because some of the hydrogen is not consumed, because we want to have hydrogen flow, it's then brought into the droplet separator.
So, and it's coming back where?
Here.
Yeah, there.
These two lines.
These two lines. Okay, right.
It's going into the droplet separator.
Yeah.
Because the hydrogen then has to exit to the recirculation pump.
Right. Okay, goes out here. Okay.
Exactly, and this is a high velocity pump, so it doesn't like liquid water. So we have to remove it here. There's a level sensor where we control the filling of this water separator.
Yes.
So as soon as this is filled, we drain the water from here. And we also, with the second solenoid, have the ability to purge the stack.
All right.
Some of nitrogen coming from the air is traveling through the membrane to the hydrogen side and is then accumulating, and we have to remove it.
Purge it from time.
That's why we purge it frequently out of this stuff.
Right. Okay.
So the hydrogen coming back from the recirculation pump is then mixed with the fresh hydrogen and goes back into the stack.
Okay. So I'm just going to turn this thing here. So basically coming out here and goes back in there. Right. So this is just the recirculation pump. So what you've not got on here is the recirculation pump and the tank system, obviously. Okay, but that's
we don't have the pumps inside because this is too much into the system because they have to fit, for example, in the installation space of the vehicle.
Yes.
And this is more difficult to integrate this directly to the stack.
Before we come to the other loops, I have one question. So I see a lot of hydrogen systems and it's all metal pipes when it's conducting, when it's carrying the hydrogen, and also it has to do with certification. So I don't see metal right here. So can you tell us how is this metal inside or what is this?
No. It's a specific plastics which is developed and tested for being capable for hydrogen. So there's really low permeation. So we don't have any hydrogen we see coming out. Also the seals are laid out to be perfectly sealing over the complete lifetime of the stack.
And all the certifications, people are big smiles, all happiness with this.
Yes, definitely. And it's also that it's better for cost reasons because metal has to be formed very in a single part, and this is all injection molded.
Okay, quickly to the other loops.
Yes.
So what about the air?
Air is coming in here.
comes in there. Okay.
It's then again underneath distributed to both stacks in parallel. So we have to supply them perfectly, both of them.
Yeah.
And then it's coming back from the stacks and exiting here. And this is now filled with water because of the reaction. It goes into a so-called humidifier. And this is transporting the water into the stream of the fresh air.
Yeah, so you want warm, wet air coming in.
Exactly.
Basically.
This is all to the membrane because the membrane likes to be completely humidified.
Okay, yeah, that's this one here.
Exactly.
Taking care of this one.
Yeah.
Okay, so that was the air and now the cooling.
The coolant is coming in here from the vehicle coolant system.
Yes.
65 to 80 degrees C inlet, going to the stacks, being warmed up by the reaction and coming back here. And then in this case, as already mentioned, is preheating the hydrogen and going back into the coolant system of the vehicle.
Okay, so you have quite a bit of the system already directly on the stack, reducing the distances, especially I think in the hydrogen loop. And okay, cool. And is this already working in some systems and so on?
This is in our production. So NM12 is a serious product. So you can directly order it from us within 12, 15, 14 weeks. You get the stack.
You get a stack
delivered.
Okay.
With this included.
Right. Okay. So maybe let's look at that a little bit. So what kind of a stack is this? And we can move this one.
It's called NM12 Twin.
Yes. Okay.
Total power 204 kilowatt.
204, okay.
So perfect already for truck integration, for rail systems, for stationary applications.
204, that would be with the two stacks.
Two stacks, exactly.
Okay.
And the advantage for the system integrator is he only has one connection. So for a system integrator, this looks like a single stack, but internally it's two stacks, two cell rows.
Okay. And is it, so again, this is the bottom, so it's kind of upside down.
Yeah.
Is it variable in the amount of cells that is?
In principle, yes.
Yeah.
The only limit is that we have to also adjust the housing.
Okay.
So if it comes to a project where we have a lot of stacks in the pipeline, then we can also adjust the housing.
All right. Okay. Okay. So tell us, Joe, a little bit, how do you see this developing? So I mean, honestly, this has been great because we saw basically the basics. Then you took us a little bit through the history. We've seen, how to make this thing feel comfortable and work. You've seen all these things. So what is next?
Next is more performance.
More performance, okay.
Because if you use a heavy-duty truck, you probably need two of those stacks to really have a 40-ton truck being perfectly running like a diesel. So that's what we do on what we call NM20. So we introduced this last year as an A sample, which is a principled prototype. We also already gave this to customers. And now we turn into the so-called B sample in the analogy of automotive. So this becomes more of a saleable product. So later in the year, so in the third quarter, we will have the B sample available. We're just currently building the first parts. And what we have from the learnings from NM20 A sample, we have introduced much more power density by 17%. So the total power is achieved with a smaller stack. And also we reduced the weight by 25%.
Again.
And also the volume of the stack is reduced by 15%. And even the outside module, what we call it, is then the housing is also 21% smaller compared to the A sample.
Okay. Right. Okay. So that's the product that will be coming later this year from you guys. I think, don't know when you're watching this video, but it will be great. Maybe it is already on the market then. I know that you guys, EKPO, you do this for like your truck applications and so on, but you also do other kinds of applications. So probably those guys wanting to work on maritime or on aerospace or so. I think you're already in some aerospace projects. They can come talk to you. Wow. Joachim, this has been fantastic. It's been a ride.
My pleasure. My pleasure.
Thank you very much for doing this, and thank you guys for watching. And if you want to get into contact with people like Joachim or find all stuff around hydrogen, go on Hyfindr.com. You see also the products of EKPO right there. I guess you guys are always open to talk. I know you guys have been in this business for a long time. It's really admirable that you do these things. Also investing, there's a heavy investment that's happening there, and also putting it all together, modularizing is helping to scale the technology, I guess, for everyone as well. So congratulations to that. Thank you to all your effort that you've put in there, and I'm sure this is helping to build a better product. Okay, bit of a long outro, but thank you very much again for watching. All the best, and thank you, Joe, again. Bye.
Thanks for having me.